Now, how to carry out an isobaric process? Okay. Isobaric means pressure has to be constant. Now, consider a container like this. One of you tell me, according to Newton's second law, what is the net force on a massless object? Newton's second law, the mathematical form is F net is equal to ma. Okay. If mass remains constant, you can write F net is equal to ma. Then how much is the net force on a massless object according to this? Make m 0, F net also becomes 0, right? So consider a system like this, a container closed by a piston on one side, movable piston, of course. Okay. Now, there will be gas. Assume these are gas molecules. They will be moving around randomly at any temperature greater than 0 Kelvin. Gas molecules will be moving around randomly. Let's say the pressure of the gas is P. Fine. Now, by means of that pressure, the gas molecules will be exerting some force on this piston outwards like this. Now, there will be pressure outside as well. Let's say the system is exposed to atmosphere on the outside. Okay. So, from outside, due to atmospheric pressure, there will be force on the piston. Okay. Now, if the piston is massless or a very light piston, okay, then you can say that the net force on the piston, if mass tends to 0, very light means mass tending to 0, then the net force also will be tending to 0. Okay. And assume it is frictionless also or negligible friction. Fine. So if you consider a very light and frictionless piston, then the net force on it will be tending to 0 means the force from the right side should be equal to force from the left side. And that is possible only if pressure on the right side is equal to pressure on the left side. So if you use a massless and frictionless piston, pressure outside will be equal to pressure inside. It has to be. Okay. If the piston has mass, then it's not necessary that the pressures are equal. Because if if an object has non-zero or significant mass, there can be a significant net force on it. Then the force on both sides need not be balanced. And if the if the piston has friction also, these two forces need not be balanced. Okay. So if it's massless, frictionless, then force on either side will have to be equal because net force has to be 0. Therefore, pressure on either side will be equal. Now, even if you supply heat to this gas, okay, usually when you supply heat to anything, temperature tends to rise and the material tends to expand. Same thing gas will also try to do. If you supply heat, it will try to expand or it will tend to expand. Pressure tends to increase. But here the piston is frictionless, massless, so the pressure inside will always have to be equal to pressure outside. Okay, so this way you can carry out an isobaric process. So you'll have to use a very light piston and almost frictionless piston to be able to carry out an isobaric process. Okay? So pressure inside the system will always be equal to pressure outside if you use that kind of a piston. And outside pressure will remain constant anyway, okay, or has to be kept constant. Then you can ensure that the pressure inside will also be constant. Okay. So that's how an isobaric process can be carried out. Fine. Let's solve some basic problems based on this. First, uh, we derived molar specific heat in an isobaric process. We got it as Cp is equal to F by 2 plus 1 multiplied with R. Generally, molar specific heat is given by the formula delta Q divided by N delta T. For the heat that you are supplying, how much temperature change is the system undergoing? If you know that, or if you have a formula for that, then you can tell how much is the molar specific heat. Okay. Now you can clearly see that molar specific heat in an isobaric process depends on the type of gas. It depends on the number of degrees of freedom, so it depends on the type of gas. Suppose there are two types of gases mixed. Okay. Now each type of gas will have a different specific heat. So let's say gas A, there are N1 number of moles and its molar specific heat is Cp1. And for gas B or belonging to gas B, there are N2 number of moles and its molar specific heat is Cp2. Okay. Now, if you put both these gases together, what will be the effective molar specific heat? Okay. At constant pressure. Let us discuss how to do this. Now, you need a relation between heat and temperature to be able to find out the effective molar specific heat, or to be able to find out the molar specific heat, right? Suppose heat supplied is delta Q. Okay. Now, some part of that heat will be taken by the first gas, some part of heat will be taken by the second gas, but the gases are put together, no? So, their temperatures will have to be equal. Okay. Initially, both gases will be at one temperature. Finally, also both gases will be at one common temperature itself. Temperature change will happen. Okay. From initial to final, there will be a change, but initial temperature of both gases will be equal, and final temperatures also will have to be equal because they are put together. Okay. Let's say the temperature change is delta T. Now, out of the heat that we supplied, some will go to first gas and some will go to the second gas. So you can write delta Q, the total heat that we supplied, is the heat supplied to gas A plus the heat supplied to gas B. Okay. Therefore, delta Q will be equal to, how do you write delta Q generally? NC delta T. So there are N1 moles of the first gas. It's a constant pressure process. Let's say the temperature change it undergoes is delta T. And for second gas, there are N2 moles. Let's say its specific heat is Cp2. Temperature change is delta T. They both undergo the same temperature change because they are put together. No, they will have to be at the same temperature always. Okay, equal temperature always. The temperature can rise, but it will have to be equal for both the gases. That's all. Now, what we need is effective molar specific heat. How do you calculate effective molar specific heat? Delta Q divided by total number of moles delta T. That is what is effective specific heat. Okay. Now from this relation that we have written here, delta Q by delta T becomes N1 Cp1 plus N2 Cp2. Therefore, if you want effective Cp, delta Q by total number of moles delta T. Now delta Q by delta T is N1 Cp1 plus N2 Cp2. Total number of moles in that system is N1 plus N2. That's all. This will be the effective specific heat if two gases are put together, if two gases of different kinds are put together. Okay, you can have three gases also. Then it will be N1 Cp1 plus N2 Cp2 plus N3 Cp3 divided by N1 plus N2 plus N3, so on. Okay, but understand the idea here because you can be asked to find out molar specific heat in many other cases also. Look at how we approached this problem. Generally, molar specific heat is delta Q divided by number of moles divided by the temperature change. So what we did was we assumed some heat is supplied and we assumed some temperature change happens. So delta Q, delta T we assigned random values. Okay. Then See, it goes without saying when there are two objects in a system and you are supplying heat, some heat will go to the first object, some heat will go to the second object. And because they are put together, they will have to be at a common temperature. Okay, initially they are at one common temperature, finally they are at another common temperature. So the change in temperature will be same for both of them. So those ideas we used and we put it in mathematical form. So out of the total heat that we supplied, some part goes to the first gas, some part goes to the second gas. Basic equation we wrote, we put that in mathematical form. Okay. And then we write delta Q is equal to NC delta T. Delta T being same for both of them, and take whatever you can take common and get the effective molar specific heat. Okay. Next, suppose you are given the PV graph of an isobaric process. Okay. In fact, from the graph itself, you should be able to identify what kind of process it is. So assume the pressure here is some 2 P naught. And let's say the volume of the gas. Okay. Assume this is V naught. And this volume is 4 V naught. The system is being taken from state A to state B. Okay. So this is the direction in which the process is carried out. So you are given an indicator diagram here. What does an indicator diagram show you? It shows you the variation of two thermodynamic variables with respect to each other. In this graph, you see the variation of pressure with respect to volume, or you can say volume with respect to pressure also. So PV graph is given to you. Okay. Uh, Fine. Let's say number of moles is N and the gas is, okay, let's take it generally only. Number of degrees of freedom is F. Okay. You will need to use degrees of freedom in internal energy calculations and all. Right. So you can see from where to where the process is carried out. Initial pressure volume are known to you, final pressure volume are known to you. And because this graph is parallel to the volume axis, pressure is not changing. So it goes without saying that it is an isobaric process. So in this process A to B, find out work done. I mean, derive expressions for work done, change in internal energy, and heat supplied. Okay. Do this quickly, all of you. I'll give you 3 minutes. Right. Listen, the general formula for work done by an ideal gas or by a gas is integral PdV. Now, in an isobaric process, pressure remains constant. So it converts to P delta V. Okay. So if you want to solve using the formula, this is how you proceed. Otherwise, from a PV graph, how do you find out work done? Integral PdV is nothing but area between the PV graph and volume axis. Okay. Basic mathematics. So this area gives you the work done. But there's one thing you need to keep in mind. Whether the sign of work done by gas is positive or negative depends on the direction in which the process is carried out. Okay. Now the area is in the shape of a rectangle. It's quite easy to calculate its area. V naught to 4 V naught is 3 V naught and the pressure is 2 P naught. So the area of this rectangle becomes 6 P naught V naught. But is that the work done in this process? Let's see. You look at the direction in which the process is carried out. It is carried out from A to B. From a higher volume, the gas is going to lower volume. Volume of the gas is decreasing. Now, gas molecules, due to their random motion, okay, let me show you a system here. Consider something like this. Okay. Now, imagine some gas molecules inside. Gas molecules, due to their random motion, okay, will always be exerting forces in the outward direction on the container. Okay, gas molecules cannot pull the walls of the container inwards. They will be pushing it outwards only always. Okay, any temperature greater than 0 Kelvin, positive pressure will be there. Gas molecules will be pushing the walls of the container outwards. But somehow forcefully, if you compress this container, okay, by doing something, you reduce the volume of this container. Okay, so the displacement of the walls of the container is inwards. Force will keep acting outwards. As long as gas molecules are moving randomly, they can only push the boundary outwards. But something is happening that the boundary is coming inwards, moving inwards. So force is outwards, displacement of the boundary is inwards. Therefore, work done will be negative. Whenever the volume of a gas decreases, work done by the gas will have to be negative. Okay. Now here in this process, clearly, as it is taken from a volume 4 V naught to V naught, volume is decreasing. Area we got as 6 P naught V naught, but if volume decreases, work done has to be negative. So the answer for work done here is minus 6 P naught V naught. Okay. Or if you use this formula, pressure multiplied with change in volume. Now see, this is the constant pressure process. The pressure we are maintaining is 2 P naught. And what is the change in volume? Final volume V naught minus initial volume 4 V naught. That way also you will get minus 6 P naught V naught. Fine. So you can proceed whichever way you want, but you need to be careful with the basics. Whether the answer is positive or negative, you need to know. We are, as I said, in physics, delta W stands for work done by the gas, not on the gas. Okay. So if the volume of a gas is decreasing, work done by the gas will be negative in any process, not just in an isobaric process. Volume decrease means work done is negative by the gas. Okay. Next is change in internal energy. Now, see, as I said, you will have a general formula and you will have a process specific formula also. It's quite possible that you don't remember the process specific formula, but the general formula you will have to remember. Generally, delta U is calculated as F by 2 NR delta T. We won't change the degrees of freedom, we won't change the number of moles. Then this is the formula for change in internal energy. Now, temperatures are not known here. The graph is a PV graph. You don't know the initial and final temperature of the gas. So there are many ways to approach this solution. You can find out the temperatures if you want. Remember, if you know pressure volume, you can find out temperature. If you know two thermodynamic state variables, you can find out the third one by using ideal gas law. PV is equal to nRT. Okay. So to calculate change in internal energy, you need NR delta T. Degrees of freedom is given to you in the problem. F, number of moles, is also given to you in the problem. Okay. So make use of the equation PV is equal to nRT. Change on the left hand side will be equal to change on the right hand side. This is, I mean, you'll have to do all this in case you don't remember the process specific formula. Okay. Right hand side N and R are constant, so I put them aside and wrote it as delta T. Actually, you are supposed to take it like if you want to go step by step, you'll have to take it as change in nRT. Okay. And if you do this for an isobaric process, we had already seen that P delta V becomes NR delta T. So in place of NR delta T, you can write P delta V. Substitute that here. Therefore, change in internal energy becomes F by 2 times P delta V. Okay. The pressure at which the process is carried out is 2 P naught and the change in volume is minus 3 V naught. Therefore, this product becomes minus 6 P naught V naught and divided by 2 is there. So the change in internal energy becomes minus 3 F P naught V naught. That's the change in internal energy of this gas. Okay. Work done was minus 6 P naught V naught. Delta U is minus 3F P naught V naught. And if you know these two, you can calculate the heat supplied delta Q minus 3F P naught V naught. That is delta U plus work done is minus 6 P naught V naught. This is the total heat supplied and it will be negative. That's fine. So actually what is happening here is heat is being removed. That's why we got heat supplied as negative. Okay. In the first law of thermodynamics, delta Q is delta U plus delta W. Remember that delta Q stands for heat supplied. And we are getting that as negative. That means heat is actually taken away from this system. Okay. Now try this problem. We know that when we supply heat to an ideal gas, some of it gets stored as internal energy and the rest gets converted to work. In yesterday's class, we saw that in an isothermal process, there is no delta U at all. Means all the heat supplied is converted to work. Nothing is stored as internal energy in an isothermal process. But in an isobaric process, the one we are discussing now, some heat only will get converted to work, not all of it. Some internal energy change will definitely happen. Okay. So suppose degrees of freedom F is given to you. So you know the type of gas, whether it is monatomic, diatomic, or polyatomic. Now, degrees of freedom are given to you. You have to find out what fraction of heat supplied gets stored as internal energy and what fraction of it gets converted to work. So you need to derive an expression for the fraction of heat supplied that gets stored as internal energy. If you know that fraction, then the remaining will be converted to work. You can tell that easily. Okay. One of you tell me how to proceed with this. Out of the heat supplied, how much is converted to internal energy is what we want to derive. What fraction is converted? So mathematically, how do we do this? I'll give you a minute. Think about it. Come up with some idea. Okay. See, we have derived formulas for all three of these terms in an isobaric process. Now, in this process, you are asked to calculate out of the heat supplied, how much is converted to internal energy or stored as internal energy, right? How you do that is internal energy change divided by the heat supplied. That's all. Okay. Out of heat supplied, how much is stored as or what fraction is stored as internal. This is what you need to do. Okay. What is the formula for delta U? F by 2 NR delta T. What is the formula for delta Q? Delta Q generally is NC delta T. Okay. But because the process is isobaric, you will have to use NCP delta T. That's all. You have to use the C value specific to this process. And we derived CP for an isobaric process. Okay, I think we did that in yesterday's class itself. It was F by 2 plus 1 multiplied with R. CP, okay, molar specific heat in an isobaric process is F by 2 plus 1 multiplied with R. Substitute that, that's all. Therefore, delta Q becomes NCP. CP is F by 2 plus 1 multiplied with R delta T. And now cancel whatever you can. N, R and delta T can be cancelled. And there you have the fraction. F by 2 divided by F by 2 plus 1, which effectively becomes or can be written as F by 2 divided by F plus 2 whole divided by 2. 2's get cancelled. F by F plus 2. That is the fraction of heat which gets stored as internal energy. For example, if it's a monoatomic gas, it has 3 degrees of freedom. That means the fraction of heat which gets stored as internal energy is 3 by 3 plus 2, 5. 3/5 gets stored as internal energy. Then what happens to the remaining 2/5? Gets converted to work. Okay. You don't have to calculate that separately. You can tell directly. So if a monoatomic gas undergoes an isobaric process, 2/5 of the heat supplied gets converted to work. 3/5 will be kept by the gas. If it's diatomic, Diatomic has how many degrees of freedom? 5 degrees of freedom. 3 translational, 2 rotational. Okay. So the ratio of, or the fraction of heat that gets converted as internal energy becomes 5 divided by 7. And the fraction that gets converted to work is only 2 out of 7 parts. So they may ask you questions like this also. Which gas does the most efficient conversion of heat to work in an isobaric process? Okay. As the degrees of freedom increase, the fraction stored as internal energy increases, the fraction converted to work decreases in an isobaric process. Fine. But again, understand the approach. Okay. You are not able to solve this problem, that's okay. But look at what you are asked. Fraction of heat supplied which gets stored as internal energy. First, make it mathematical. Fraction of heat that gets stored as internal energy means delta U divided by delta Q. And then we wrote the formulas for those process specific formulas we wrote, divided whatever, cancelled whatever is common, and we ended up with this result, F divided by F plus 2. Okay, fine. So far we have discussed two basic thermodynamic processes, isothermal and isobaric. Okay. The next common thermodynamic process is an isochoric process. Now, what happens in an isochoric process? Isochoric means the volume of the gas is kept constant. It's not allowed to expand, it's not allowed to get compressed also. Okay, volume is kept constant. And it's very easy to understand how to carry out such a process. Just take a container whose volume does not change. Okay. It can exchange heat with the surroundings. Okay. But the volume should not change. Simple. So fixed piston. Don't allow the piston to move. It should not move outwards or inwards. So the gas cannot expand. It cannot get compressed also. So if you use a container of constant volume, you can carry out a constant volume process. Fine. So as usual, we'll have to draw the graphs for this process, then derive formulas, process specific formulas for delta W, delta U, delta Q. We'll do that quickly. Now we know PV is equal to nRT. Being an ideal gas, the gas will definitely have to obey this relation. Now the volume is kept constant. N and R are anyway constants. So you can say pressure is equal to nR by V multiplied with T. nR by V is a constant. So pressure is some constant multiplied with temperature. Therefore, pressure becomes proportional to temperature. Okay. So at constant volume, pressure of a gas is proportional to its temperature. And we are getting this from ideal gas equation. In an ideal gas equation, temperature must be in Kelvin. Okay. Absolute temperature. So here also the temperature has to be in Kelvins only. Then pressure will be proportional to temperature. That is okay. That is what happens in an isochoric process. Fine. Next thing we do is draw the graphs for such a process. Isochoric volume is kept constant. So suppose you want to draw the PV graph. The first graph we always draw is PV graph. Let's say you take pressure on the y-axis and volume on the x-axis. Volume is kept constant. So whatever you have on the x-axis is constant. If x is constant, that means the graph is a straight line parallel to y-axis. Simple. So at constant volume, pressure may increase or decrease depending on what you do with the gas. The graphs will look like this. Let's say this is carried out at fixed volume V1, you get a graph like this. If you carry it out at some other volume V2, you get a graph like this. Quite simple. Yeah. Next, pressure temperature graph. Now, volume is kept constant, but pressure and temperature are both allowed to vary. And we have just seen that if volume is constant from PV is equal to nRT, pressure becomes proportional to temperature. If Y is proportional to X, okay, little bit of mathematics as I said, the graph will be a straight line passing through the origin. P is equal to nR by V multiplied with T. We are taking pressure on the y-axis. So nr by V will be the proportionality constant. Temperature is being taken on the x-axis. So the proportionality constant between y and x is what you call as slope of the graph. Y is equal to mx. So the slope of the pressure temperature graph in an isochoric process, a process where volume remains constant, will be nr by V. So greater the volume, lesser the slope. Fine. The graph has to be a straight line passing through the origin. So it goes like this. We don't actually make it pass through the origin. It'll be like this. Let's say this is carried out at volume V1. Okay, at a fixed volume V1, if you see how pressure varies with temperature, let's say you got a graph like this. For the same gas, at another volume, if you carry out the process, the graph could be like this at a different volume V2. Now, what's the difference between these two graphs? The slope is different. First one has greater slope. Now we know that slope is nr by V. If pressure is on y-axis, temperature is on x-axis, then slope is nr by V. Greater the volume, smaller the slope. Okay. So the second graph, the one drawn for V2, has smaller slope. That means V2 must be greater volume. Okay. V1 must be lesser volume. So based on graphs, you should be able to tell which was carried out at under which conditions. Okay. Such questions are quite common. So understand the approach. If you want to comment on which volume is greater, you need to know the relation between pressure and temperature, the formula or the equation between them. Based on that, you can tell how much is the slope or what is the formula for slope. And from the formula for slope, you can tell which one corresponds to greater volume. Okay, so this is the pressure temperature graph for an isochoric process. PV is equal to nRT, so pressure becomes proportional to temperature. Next, volume temperature graph. Quite simple. Volume remains constant, temperature varies. So depending on which axis you take volume on, you'll have to draw the graph. Let's take temperature on y-axis, volume on x-axis. If since volume is on x-axis and this is a constant volume process, it becomes x is equal to constant again. X is equal to constant represents a graph which is parallel to y-axis. Okay, straight line parallel to y-axis. So temperature is allowed to change. Volume is not allowed to change. So depending on the volume at which the process is carried out, you can get a graph like this. Simple. Okay, so we have drawn all three graphs for an isochoric process. Next thing to do is to derive expressions for delta U, delta W, delta Q and all. Okay, first, work done in an isochoric process. General formula for work done is integral P dV. Now, being an isochoric process, the volume is not allowed to increase or decrease. Now, if volume is not being allowed to increase or decrease, it means the effective displacement of the boundary is zero, boundary of the container. Gas exerts pressure, gas is exerting force, but displacement is not happening. Or on one side, positive displacement may be happening, on the other side, negative displacement must be happening so that the volume remains constant. So basically, there's no change in volume. So dV tends to zero. And since dV tends to zero, integral P dV will also become zero. Therefore, no work is done by the gas in an isochoric process. What does that mean? That means all the heat you supply gets stored as internal energy itself. None of it will be converted to work. Okay, that is what happens in an isochoric process. Okay, so delta W is zero. Always in an isochoric process, delta W has to be zero. Next, delta U, change in internal energy in an isochoric process. If you see, general formula for delta U is F by 2 nR delta T. So if you know the temperature change, you can substitute that and find out the change in internal energy. Now let us derive a process specific formula. Now we know PV is equal to nRT. And we also know that the change on the left hand side should be equal to change on the right hand side. Okay. This time Volume is constant, pressure can change. So the left hand side becomes V delta P. Okay. It's like P final, V final minus P initial, V initial. V final, V initial are same. You take it common, you will be left with V delta P is equal to right hand side becomes NR delta T. So NR delta T can be replaced with V delta P. You can substitute that here if you want. And the process specific formula becomes F by 2 multiplied with V multiplied with delta P. Okay. So as I said, you don't have to remember this process specific formula because for each process you'll have a different formula. You may get confused in the final exam, but you should know how to quickly derive it. Practice these derivations once. Okay. Not once, as many times as needed. You should be able to derive all these on your own. Okay. Then you can solve any question in thermodynamics easily. Okay. So that's how you find out change in internal energy in an isochoric process. Next is delta Q. We know delta Q is delta U plus delta W. Delta W is 0 in an isochoric process. It's always 0. Therefore, delta Q is equal to delta U itself. So you can write it as F by 2 NR delta T itself. Or you can also write it as F by 2 as we just derived. V delta P. Okay. Now you see that we have a relation here between heat supplied and temperature change. If you have that relation, you can derive the molar specific heat of that process. Okay. Let us do that. Molar specific heat. And what kind of process is this? Isochoric process. So at constant volume, we call it as CV. Molar specific heat symbol is C. Since the volume is constant, we call it as CV. Now, C generally is delta Q by N delta T. Now, in this case, it becomes delta Q divided by N delta T, and it becomes equal to what? If you send N this side and delta T this side, what will you be left with? F by 2 multiplied with R. Therefore, CV of any gas is given by the formula F by 2 multiplied with R. Cp was F by 2 plus 1 multiplied with R. Cv is F by 2 multiplied with R. In fact, in chemistry, you must have derived or come across this equation. Cp minus Cv is equal to R. Okay, there is an elaborate derivation also for it. Uh, I don't know if you have done it or not. Okay. Now we got Cp as F by 2 plus 1 into R. This we derived yesterday. Cv we are now seeing that it is F by 2 multiplied with R. Obviously, if you subtract these two, it becomes equal to R itself. Okay. So this way also you can prove that Cp minus Cv is equal to R for an ideal gas. Okay. Again, needless to say, Cv depends on the degrees of freedom. So it varies from gas to gas. So Cv for monoatomic gas will be 3R by 2 because monoatomic gas has 3 degrees of freedom. 3R by 2. Cv for a diatomic gas. Diatomic has 5 degrees of freedom, so 5R by 2. And for polyatomic nonlinear molecules, it will be 6 degrees of freedom, so 6R by 2, that is 3R. Okay. So it depends on gas, varies from gas to gas. And today we solved one problem, right, where we considered a mixture of gases, N1 moles of one type of gas having Cp1, N2 moles of another type of gas having Cp2, and we derived the effective molar specific heat. We can do the same with Cv also. Okay. And suppose something like that is given to you. N1 moles of one gas having Cv1 put together with N2 moles of another gas having Cv2, then the effective Cv becomes N1 Cv1 plus N2 Cv2 divided by N1 plus N2. So you can find out the effective molar specific heat of a combination also or a mixture of gases also. Fine. The next thing we talk about is bulk modulus of that process. Yusuf, can you tell me the general formula for bulk modulus? Like by definition, what is the basic formula for bulk modulus? Bulk modulus is generally volume stress by volume strain. And like we discussed in the last class, mathematically it's written like this. Okay. So it becomes minus V delta P by delta V. In thermodynamics, we take it as minus V dP by dV. And where do we get this from? We get this by differentiating the ideal gas equation. Okay. Now you don't have to do it actually because we are talking about an isochoric process. In an isochoric process, volume does not change. That means change in volume dV will be zero or tending to zero. Okay. If dV tends to zero, the denominator tends to zero, then the bulk modulus in an isochoric process will be tending to infinity. What does that mean? See, as I said, or as we know, bulk modulus or any modulus of elasticity for that matter, Young's modulus or shear modulus or bulk modulus, they give you an idea of the rigidity of the system, okay, elasticity of the system. Greater the modulus of elasticity, more difficult it is to deform that system. Now, this is an isochoric process, means the volume is not changing at all. So you can say that the gas is incompressible. Okay. Even though you are increasing the pressure, the gas does not get compressed. What does that mean? It is not possible to deform the system. So it should be having infinite elasticity, infinite amount of elasticity. So bulk modulus will be tending to infinity in an isochoric process. Okay. So simple only, volume remains constant. Based on that, we discussed all the things that we do for any other, uh, any thermodynamic process. Okay, let's solve a few questions based on this isochoric process. First one. Okay, try this. In an isochoric process, what fraction of heat supplied gets stored as internal energy? Try this. I'll give you 2 minutes.
Say so then
And
we can substitute delta. We can move q to the side. Delta u
huh,
divided by q. And then we can substitute delta q by no delta u by q. So q by q is equal to 1.
that's all. Correct, correct. So basically what you are asked to calculate is delta U divided by delta Q. And as you rightly said, using the first law of thermodynamics, you can say that since it's an isochoric process, work done is zero. So all the heat supplied gets stored as internal energy itself. So what fraction gets stored as internal energy? 1. Okay, 100%. What fraction gets stored to work, converted to work? The answer will be 0. Okay, fine. Let's try another question based on a graph. Okay, let's say volume on the x-axis and there's pressure on the y-axis. It's an isochoric process. So volume will remain constant. Assume the volume is V naught and pressure can change. Let's say the pressure increases from an initial value P naught to a final value, say 3P naught. Okay. You can see the direction in which the process is carried out. And see, the graph is a straight line parallel to y-axis. So there will be no area between the graph and volume axis at all. See, had the graph been like this, there would have been some area under it. But since the graph is a vertical straight line, you won't have any area between the graph and the horizontal axis. So since there's no area, you can say work done is zero. Okay, we know that anyway. In an isochoric process, work done is zero. So suppose there are n number of moles, n is given to you, and degrees of freedom f is also given to you, and this is the process. Pressure is increased from P naught to 3 V naught. Derive an expression for heat supplied in this step. Try. Tell me what different ways are there to calculate delta Q? One is to use the first law of thermodynamics. Another way is to write NC delta T. Okay. Like you have very few formulas in thermodynamics. You just have to think of which is the appropriate one to be used in a particular situation. Okay. You can do it both ways actually. Now see clearly this is an isochoric process. Work done is zero. So whatever is the change in internal energy, the same will be the heat supplied. Okay. And for internal energy, we have a general formula. F by 2 nr delta T. And in an isochoric process, nr delta T changes to V delta P. So if temperature had been given, you could have used nr delta T directly. But the graph is in terms of pressure and volume. So we use V delta P. Simple. So F by 2 times what is the volume at which it is carried out? V naught. And what's the pressure change that is happening? P naught to 3 P naught. So the change in pressure is 2 P naught. The twos cancel. The answer is F P naught V naught. That is the change in internal energy. Same will be the heat supplied. Okay. Suppose you used NC delta T. N. You have to use the C value, molar specific heat, for this particular process. Molar specific heat at constant volume we just derived is F by 2 multiplied with R. That will have to be used multiplied with delta T. You get the same answer F by 2 nr delta T, which can be written as V delta P, and it will be equal to F times P naught V naught. Is this clear?
Yes, sir. Yes, sir.
Okay, fine. Right. So, okay, that is enough about isochoric process. So we discussed isothermal, isobaric, and isochoric. Tomorrow's class will discuss another thermodynamic process called adiabatic process. Okay. And if time permits, we will talk about something called a general polytropic process also. But adiabatic process, there will be more derivations involved. So a slightly tricky process, you can say. Like in these three processes, isothermal, isobaric, isochoric, one of the thermodynamic state variables was kept constant, temperature or pressure or volume. In an adiabatic process, none of them will be constant. Okay, so that is what makes it slightly tricky. We'll discuss that in tomorrow's class. Okay, thank you.